Welcome to 6.2 Properties of Logarithms. In part 1, we're simply going to look at all of the properties and do some examples with them. So the first property, and I took this straight from your textbook, the first property is the inverse property of exponential and logarithmic functions. We've already discussed that exponential and logarithmic functions are inverses of one another. So we need to let b be greater than 0, and of course it cannot equal 1, that's our base. Then we know that b to the a equals c, if and only if log base b of c equals a. This first part is simply going from exponential form to logarithmic form, something that we've already discussed and work with. Then the next two are things that you had on a previous assignment that maybe you figured out or maybe not, but this is a property that when we have log base b of b to the x, that is simply a way to write x because it's b to the what equals b to the x, and that's x. That's for all x. And then the same thing holds. Another way that we could write a number x is b to the log base b of x. And that works for all x greater than 0 because whatever we input to a log must be positive. So let's look at a few examples of these. Our first one is simply going from exponential form to logarithmic form, so I will do just a simple example for this. We could say that 2 cubed equals 8. And that means if and only if, IFF, log base 2 of 8 equals our exponent of 3. So again, simply going from exponential form into logarithmic form and back the other way. This if and only if, IFF, is a logical and mathematical sort of statement in theorems showing that we can go both ways. So we could also have written the statement with log base b of c equals a first, if and only if b to the a equals c. This next property can be used in a lot of different ways, such as we could start with x. So let's say we have the number 5, and let's say let 5 equal x. I'm just coming up with a random number. So we could say that 5 equals any b, right? If I let log, let's say we said log base 3, we could write 3 to the 5th. And this is a true mathematical statement. Log base 3 of 3 to the 5th equals 5. What's another way that we could write this? We could really come up with any b value. And we could say that just log base 10 of 10 to the 5th does equal 5 as well. Another base that we could use just for an example would be 2. So log base 2 of 2 to the 5th is another way to write 5. We could also use natural log. Remember, natural log has a base of e that we don't write. So if we use natural log, we could say ln, of course base e, which we don't write, of e to the 5th equals 5. Again, I'm just picking 5 as a random number. We could use any number. So I'll do one more example, and we don't necessarily need to let x be 5 anymore. We could also say that log base 7 of 7 squared, that equals 2. Our last property is similar to this, and if we take a look at this last one here, we have b to the log base b of x equals x for all x greater than 0. So again, I'll let x equal 5, just a nice positive, easy number to work with. And then b can be anything. So for example, we could have 3 to the log base 3 of 5, that equals 5. We could have another example. We could say 10 to the log, of course, base 10 of 5 equals 5. Another example that we could have, and again, x does not necessarily have to be 5. Another example that we could say is that 8 to the log base 8 of 12, that equals 12. So these are 3 properties of logarithms, and we'll actually use, I don't recall if we end up using this one, but we end up using this in order to solve a lot of equations, which we'll get to especially in the next sections of chapter 6. And then we'll end up using this one here later on just for certain justifications. next properties deal with the fact that exponential and logarithmic functions are one-to-one functions of one another, meaning that an exponential and logarithmic function are going to pass both the vertical and horizontal line test. So not only are they inverses of one another, they are one-to-one functions, meaning each on its own is a function. So once again, we want to let f of x be b to the x, our exponential function, and g of x is its inverse, log base b of x. Of course, where b needs to be positive, but not 1. Then we can come to the following three conclusions. F and g are one-to-one. And that can just be seen on a graph. They both pass the horizontal line test and, of course, the vertical line test because they're functions. And then these next two, which may seem obvious, but we are going to be using them, they're the equality properties. So b to the u equals b to the w, if and only if u equals w. So that makes sense. Something equals the same thing. And then this right here is mathematical notation that says that u and w are both elements of the set of real numbers. So both u and w are real numbers. Then, similarly, log base b of u equals log base b of w, if and only if, once again, u equals w, so something equals itself. And then, of course, u and w have to be real numbers once again. However, because we're inputting them into a log function, they both have to be positive. Not going to go super in depth on examples of these ones, but let's say, b needs to be greater than 0 and positive. So let's allow b to be 3. So 3 to the 4th equals 3 to the 4th. It seems obvious, but if we're solving, right, so let's say we had 3 to the x equals 3 to the 4th, you know that by this equality property here, that x has to be 4. So that would be the reason that we need this. And this can get a little more complex with the bases being slightly different. So we'll see that later on when solving exponential functions. Moving down to this next one, I'll give another quick example. So let's say we have log base 10 of 7. If u and w equal each other, then log of x, we know that x would have to be 7. So just coming to those conclusions using these equality properties. Next here I made a little graphic organizer of the three main properties of logarithms. These are the algebraic properties, and these are the ones that we're going to use the most frequently. And the first one is called the product rule for logs. And the product rule, move those a little bit, says this, that log base b of u times w, so that's why it's a product rule, means that you can separate them and write it as a sum of the two factors separated. So log base b of u times w equals log base b of u plus log base b of w. In this first example, we have log base 10 of 3 times x. So u is 3 and w is x. We can rewrite this using the product rule for logs as log of 3 plus log of x. Now, if we could simplify either one of those any more, then we would. However, we do not know 10 to the what gives us 3. Like, this is not some nice multiple of 10 that we could figure out. So this is where the simplification ends. So we have expanded this logarithm using the product rule. We can expand this next one as well, but this one doesn't really look like a product. It just looks like a difference. However, we can rewrite this using factoring because x squared minus 4 is the product of x plus 2 and x minus 2. That's the difference of squares. So this is really x plus 2 times x minus 2 all inside our natural log. And now it is a product where u is x plus 2 and w is x minus 2. So we can now expand it using the product rule. So this is really the natural log of x plus 2 plus the natural log of x minus 2. So the product rule and the other two algebraic properties that we'll get into work for both log logs and natural logs, ln. So getting into our next rule here, our next rule is called the quotient rule. And the quotient rule is very similar to the product rule in that with the product rule, when we had a product, we could split it into basically a sum of the two separate factors of that product. The quotient rule has a quotient or a fraction, and we can split it into a difference. So for example, well actually let's look at it. So we have log base b of u over w, a quotient, and that equals log base b of u minus log base b of w. For example, we have log base 3 of 8 over x. 8 is our u value, x is our w value. So we can rewrite this as log base 3 of 8 minus log base 3 of x. And that's all I have to say about the quotient rule. Now we have our very last property of logs, and that one is called the power rule. So the power rule is all about the exponents outside of a log. So in this case, we have the log base b of u to the w. We can actually bring that w, that exponent, out front and write it as w times log base b of u. So for example, we have log base 10, so log of x to the 4th. This 4 is our w, while the x is the u value. So we can bring that 4 out front and write it as 4 times the log of x. Now why does this work? Well, what we can do is write log of x to the 4th. We could really rewrite that as log of x times x times x times x, because that's what x to the 4th is. Then using the product rule, we can really rewrite this as log of x plus log of x plus log of x plus log of x. Well, combining like terms, we have 4 log of x. So the power rule really relies on the product rule to work. So I showed sort of a non-sophisticated mathematical proof, just kind of writing out an example. There are good proofs of product and quotient rule. I'm not going to go through a lot of time with explaining them on this video, but if you are interested, there's some interesting ones that you can find online. But I just think the one for the power rule is kind of neat, how it depends on the product rule. So anyway, the power rule deals with exponents, while the product and quotient rule deal with products and quotients, fractions, respectively. We can use these 3 algebraic properties of logarithms in order to expand and to simplify logarithmic expressions and equations. Let's take a look at these first 2 here. We want to expand each one of these logarithmic expressions or terms using the properties of logs, and then we want to simplify as much as we can. So in our red problem in number 1, we have the natural log of a quotient, a product in the denominator, e times x, and then we also have a power. So we're going to actually be using all 3 of our properties in one problem. So the first thing that we want to do is use the power rule and bring that 2 out front. So we can write this as 2 ln of 3 over e times x. I'll put the little dot there to show that that's a product in the denominator. Well then, what we want to do is expand because we have a quotient here. We have a quotient, and using the quotient rule says, so this 2 is going to be multiplied by everything. So the quotient says that we could do the ln of 3, we don't really need an extra parentheses there, minus the natural log of e times x. So we use the quotient rule that says that the log of u over v equals the log of u minus the log of v. Now v happens to be more than one term, so we'll get there next. So what we've done so far is the power rule first, then the quotient rule second, because we have a quotient here. Now, this term is simplified as much as it can be. However, this term is not. We still have a product on the inside of our log, our natural log. So using the product rule, we have ln of 3, then minus, we want to use the product rule. So we're going to have the natural log of e plus the natural log of x, since the product rule says that when you have the log of u times v, it's the log of u plus the log of v. I had to put it in parentheses here because we're subtracting more than one term. So simplifying this on the inside, all of the ln of 3 minus the ln of e minus the ln of x. Can we simplify any one of these terms? We should see that the natural log of e can be simplified. Because natural log has a base of e, using our properties, this is really e to the first. The b value is e here, and this is also e. The natural log of e, or e to the first, is just 1. So this term here is just 1. So we have 2 ln 3 minus 1 minus ln of x. We could keep going if we wanted to. This is a fine place to stop, but what I'm going to do is multiply the 2 through. So we'll have 2 ln 3, and I'm also going to write the natural log terms first. So then it's minus 2 ln of x, then it's minus 2 when we simplify through. So either one of these is fine for simplifying, but what we've done is expanded, and we've simplified any terms possible. So the ln of e was 1. This next example here in blue is the log, and it's base 10. So the log of the cube root of this entire quotient, 100x squared divided by y times z to the 5th. Note that the z is the only thing raised to the 5th because yz is not in parentheses. What we can do first is actually rewrite this logarithm so it looks like the first one and it's raised to something rather than being a cube root. So a cube root is really being raised to the 1/3 power. So we can rewrite this as such. Then we can use the power rule and bring that 1/3 out in front to simplify it even more. Then we realize that overall we have a quotient. We have a numerator and a denominator inside of our log. So the quotient rule says that when we have the log of u divided by v, we can rewrite it as the log of u, so u being 100x squared, minus the log of v, v being the denominator, yz to the 5th. Now from here, we note that each one of our logs still is a product. And using the product rule, when we have the log of u times v, we can rewrite it as the log of u times the log of v. So this is the log of 100 plus the log of x squared. And then this is minus both logs. So we're going to expand this using the product rule. It's the log of y plus the log of z to the 5th. And I put that in parentheses because we're subtracting more than one term. So in this next step, what I'm going to do is simplify any terms that I can, and then also distribute this minus sign through. What we also can do is note that we can use the power rule again on these logs. This 2 can come out front of this term, and this 5 can come out front of this term. The first thing we want to simplify is realize that log 100 can be simplified. This is asking us 10 to the what gives us 100. Log 100 is 2. We can bring the 2 out front of the next term using the power rule. Then I'm going to distribute the minus sign, so it's minus log of y. And minus, here, using the power rule again, we can bring the 5 out front. Minus 5 log of z. I don't see us being able to really do anything else, so at this point we have expanded and simplified as much as we could. Yes, you could technically multiply the 1/3 by all the terms, but either way is totally fine, just like I did here. I just sort of ran out of room. So we've used the properties of logs to expand a single logarithm, but what if we have more than one term and we want to actually write it as a single logarithm, log of something? So the first thing we have to make sure is that all of our logs in our expression have the same base. And in this first problem in red, they do. So we have log base 3 of x minus 1 minus log base 3 of x plus 1. Well, this looks like this is the quotient rule already expanded. So we can rewrite this as a single log base 3 of a quotient, where this is u and this is v, going backwards now with the quotient rule. X minus 1 is our numerator, and x plus 1 is our denominator. We cannot simplify this anymore, and we already have it written as a single log. Only one log now. So we have finished this problem. In number 2, what we want to do is get both terms to have log base 2. That's the only way to write them as a single log. So this 3 right here needs to be written as log base 2. And this is when we're going to go back to that property that looks like this. So for this 3, we're going to end up using this property that says log base b of b to the x equals x. It's what we looked at earlier in the video. So we can rewrite 3 as log, and we want it as base 2 because that's what our other term has. So log base 2 of 2 cubed. That is the alternate way to write 3. That's how I'm rewriting the number 3. So they both have a base of log base of 2. So now we have two terms and they have a log base of 2. That means we can now use those algebraic properties of logs to combine them into a single log base 2. So this is the expanded form of the product rule. The first thing I want to do is get this 4 where it belongs. This is the expanded look of the power rule. This 4 can get put back up into its exponential place. So this term can be written as log base 2 of x to the 4th, using the power rule just backwards. So plus log base 2 of 2 cubed. Now, instead of actually writing it as 2 cubed, to simplify it as much as we can actually just write this as 8, which is what 2 cubed is. Our final step now can use the product rule to write it as a single log. So this is log base 2 of u plus log base 2 of v. That really means we can rewrite this as log base 2 of u times v, which is x to the 4th times 8, or the way we want to write it is the 8 first, just like that. So we have now combined this and written as a single log using our algebraic properties of logs plus this other property of logs.